Good morning, good afternoon, good evening, everyone, whatever time you're watching this clip. Here's another question that's a very, very common question on exams and tests. And it relates to the last part of what we're doing in this series on our YouTube clips to do with equilibrium, things that hang. Now, there could be street lights hanging off tensional cables on either side of the road. It could be a picture. It could be I've chosen for this calculation a pop light that I suppose it's a bit unrealistic because it's only being supported by two cables. They both seem to be the same length. I'm just going to make some numbers up. Let's say this pop plant has a mass of 5 kilos. So let's just say the weight of the pop plant is 5 kilos times 9.8 to convert to a force. All right, now if we look at the situation, we can see that once again we've got a tension in each of these two cables that if these angles are the same, those two tensions are going to be identical. All right, and we're going to frame up the question to make these two tensions identical because these angles are both the same. All right, now I'm going to suggest that in this question in a test, you'll be given 25 degrees here. I'm just making this up as we go. Which means if we look at all the angles of this triangle over here, we can see that this angle here is going to be 77.5 and this is 77.5 as well. Let me just check that. Yep, that's about right. Okay, now the reason why this whole situation is in a situation of equilibrium, we can look at these two tensions and we can break them into their horizontal and vertical components. Let me do that in red pen. So, the vertical component of the tension in the left-hand cable can be shown to be a vector that looks like this, and the horizontal component is going to look like this. So that kind of makes sense. Okay, this tension in the left-hand cable is upwards and to the right, so therefore we've got an upward vertical component and a horizontal component to the right. You do exactly the same for the left-hand cable, because these two vectors are going to be identical, like so and like so. All right? Now, the first thing that we have to just remind ourselves is the fact that this pop line is not accelerating up or down. Well, I hope it doesn't, and if it does accelerate down, I hope you're not standing underneath it, because you're going to get hit. So let's just say it's not accelerating up or down. It's static. It's in a situation of equilibrium, nor is accelerating to the left or the right. Now, the fact that it's not accelerating up or down means that this force of this component plus this component must be equal to the weight of the pop line. Now, let's work out those two components to start off with. Okay, I've got a force here of 77.5, which means that the angle that's subtended over here is 12.5 degrees, and we've got 12.5. Looks terrible. 12.5 degrees. Which means the magnitude of the vertical component on the left-hand side is going to be equal to t cosine 12.5, t cosine 12.5. The horizontal components are really not important for this question, but we'll put them in anyway. We're going to get t sine 12.5 and t sine 12.5. Pause the video if you need to and just examine what I've done here. But very obviously, t sine 12.5 is equal to t sine 12.5. T sine 12.5 to the left, to the right, is equal to t sine 12.5 to the left. That makes sense. But we don't need that for this question. However, that idea might become important in another question that's related to this sort of scenario, where these two angles are not the same. We'll explore that in another video. All right, so what I've got here, I'm just going to touch my screen to make sure that we don't go into sleep mode. Clearly, t cos 12.5 plus t cos 12.5, which gives us, let's say, to find t. 2, let's do it again. Let's stick with our laws of equilibrium. The sum of all forces up must be equal to the sum of all forces down in this question. So therefore 2 t cosine 12.5 must be equal to the weight of the pot plant, which is 5 times 9.8. Therefore, t is going to be equal to 5 times 9.8 divided by 2 times cosine 12.5. And what I get is tension is going to be equal to 25.1 newtons. All right. The tension of this cable is 25.1 newton. The tension of this cable is 25.1 newton. And this is very, very typical of a question that you might get in a test or an exam. Remember, it could be a street sign, or say street lights supported by 2 cables. It could be a picture that the cables where the string holding the picture up is in the other direction. But the principles are exactly the same, and they're very straightforward. Thank you.